Funding for this program was provided by the Annenberg CPB project.
The momentum of an object is equal to its mass times its velocity. When no external forces act on a system, the total momentum is constant. This principle is called the conservation of momentum.
One of the effects of the trial of Galileo was to expel the scientific revolution from Italy. It eventually came to rest, of course, in the person of Isaac Newton in England. But on its way north, it stopped off in France for a while to visit René Descartes. I haven't said much about him up to now because I didn't want to put Descartes before the course. Descartes understood straight lines. That might not seem like much to you, but it led to the invention of Cartesian coordinates, which are named after Descartes, although he didn't invent them, and to the principle of inertia, which Galileo hadn't quite gotten straightened out. Descartes was a great scientific optimist. He thought that we would come to understand everything we needed to know in a few years if we would just follow a few rational principles, which, of course, he was kind enough to lay out for us. One thing he deserves credit for is the idea of the mechanical universe. That is, a universe that would inexorably work out its destiny following precise mechanical laws. It was rather like a clock or one of those exquisite mechanical toys the craftsmen of his era used to make. But the analogy broke down in one important respect. A clock has to be wound up from time to time. And Descartes did not want that kind of intervention from the creator of his universe. And so he needed some principle that would keep the universe running forever. And the one he hit upon was the idea that the total quantity of motion in the universe was fixed. That is, if one thing slowed down and came to rest, another body would have to speed up and start moving. That idea eventually became the law of conservation of momentum. And that's our subject for today.
These men live by certain laws. Sometimes beyond the gambling statutes of the city and county of Los Angeles, but well within certain laws of classical mechanics. They make their living off the art and science of pocket billiards. Not every man enters Chalky's Billiard Academy to illustrate the conservation laws. Not every man here fully appreciates the fact that, win or lose, classical mechanics governs the game of pool. Most walk down Chalky's narrow stairs to shoot a stick, or to profit from the experience by some other means. But odds are, when certain laws of physics are applied just right, every man here fully appreciates the effects Of course, while a billiard ball may obey those laws perfectly, the principles behind them didn't originate in Chalky's Billiard Academy. Some of those principles, like the game of pocket billiards itself, originated in France. As a youth in the Catholic France of the early 17th century, René Descartes came to love the trappings of mathematics as the workings of God. He loved the power of a finely reasoned argument and the glorious feeling when a concept could be understood in the absolute. But Descartes lived at a time when, not unlike today, the glories of God and the power of reason didn't always exist in perfect harmony. In 1600, when 4-year-old Descartes was just beginning to come to terms with the Europe around him, a scholarly monk named Giordano Bruno was burned at the stake for, among other things, his beliefs in the Copernican system of the universe. Eventually, Descartes, like Galileo, was a Copernican. But unlike Galileo, who was tried in Rome for expressing himself to one and all, Descartes withheld publication of similar views when they flew in the face of the Mother Church. To some scholars, Descartes is remembered as a cowardly hypocrite. Others remember him as a sincere, devout, and devoted Roman Catholic. As for Descartes himself, he probably just remembered what happened to Giordano Bruno. In any case, it was Descartes who first enunciated this principle. The total quantity of motion in the universe is constant. If a body is not interfered with, it will move at constant speed in a straight line. That's the law of inertia, Galileo's idea, perfected by Descartes. But when a body does meet others, it isn't merely brought to rest. It transfers its motion to the other bodies. The total quantity of motion is conserved. Though Descartes was the first, the essence of his quantity of motion was in fact expressed better by Isaac Newton. Of course, as competitive as he was, it's doubtful whether Isaac Newton ever challenged a colleague to a game of pool. His challenges were to the intellect alone, and none of his expressions was more powerful and moving than his idea of momentum. In his classic work, The Principia, he wrote, "The change in motion is proportional to the force impressed, and it is made in the direction of the straight line in which the force is impressed." Newton used the word motion to mean momentum, or in modern terms, the velocity of a body multiplied by its mass. In his own field, Newton chose to express most of his powerful ideas with classical geometry, using geometric figures and ratios between quantities. But he was skilled enough to know that his laws could be expressed as differential equations. According to Newton's second law, the impressed force is equal to the rate of change of momentum. Newton's second law: moving, powerful, and everywhere in the universe, an idea with an enormous impact. Interactions around this table are complex subjects of social science. Interactions on this table, however, are purely physical in nature and comparatively easy to explain. Again, according to Newton, a single particle of some definite mass has a momentum equal to m times v, and the change of momentum can be expressed by a differential equation. Force is the rate of change of momentum. Of course, if there are no forces operating, the derivative is equal to 0. Therefore, the vector p is constant, which means the motion of the thing itself is constant. A body with no forces acting on it will continue moving at the same speed in a straight line. This is the law of inertia, Newton's first law. But when billiard balls collide, each one applies a momentary force to the other, causing its momentum to change. Here, Newton's third law gets into the action.
The forces the balls apply to each other are equal and opposite. The change in momentum of one ball is, therefore, equal and opposite to the change in the momentum of the other. The total momentum of the two balls taken together does not change at all. It's constant. In fact, this new law applies not only to two balls when they strike, but to any number.
And not only to the billiard balls themselves, but to the very atoms of which they are made. And even in the inner parts of the atoms, the electrons and neutrons and protons, right down to the ultimate constituents of matter itself, momentum is always conserved. But there's an easier way to win the game than to keep track of the countless electrons and protons and neutrons in each billiard ball. Even though each ball is composed of atoms and smaller parts, applying equal and opposite forces to each other, each ball behaves as if it were a single body with all of its mass concentrated at a single point. That point's called the center of mass, and in this situation, it's one of the more explosive ideas in physics. The center of mass is the point to focus on when calculating the velocity and acceleration of a compound body. When no net outside force acts on a compound system, no matter what happens to its individual parts, the center of mass continues to move at constant speed in a straight line. In deriving his second law, Newton might have imagined a collection of compound bodies, not necessarily touching each other. Two bodies of nearly equal mass. Or perhaps better yet, two bodies like the Earth and the Moon. He knew hidden forces were at work up there. Gravity, for example. Conversely, he could imagine that external forces were not at work on such a system. Then the system wouldn't be accelerated. Its center of mass moves with a constant velocity. If the planet pulls on its moon, then the moon pulls on the planet with an equal but opposite directed force. The vector sum of the two forces and the derivative of the momentum of the bodies are equal to zero. If the derivative of something is equal to zero, that something is constant, and that constant, the sum of the momenta of all the bodies, is a conserved quantity. It always stays the same. This law applies to two bodies or three or more bodies throughout the universe, past, present, and future. The good ship Newtonia, Nova Fleet defender of the mechanical universe.
What a dump!
The good ship Newtonia. Perhaps not quite the image of a Star Wars defense system. But when it comes to maintaining the physical laws of the universe, who's to say she's not up to the task? Using force when necessary, and alas, it always is, Newtonia fires an astroshell in defense of the laws of the mechanical universe, including, of course, the law of conservation of momentum. Newtonia recoils. This action and reaction should not be mistaken for timidity under fire. On firing, when the astroshell is blasted off, Newtonia recoils because the total momentum of any system remains constant. So look at it this way. When the shell is fired, it zooms one way, and the good ship Newtonia zooms quite the other. But no matter what direction, no matter how intricate the system, and no matter its specific components, the conservation of momentum remains in play. And for that matter, so does the conservation of energy. That's because, although it takes many forms, energy, like momentum, is always conserved. Whether it's in the form of potential energy, U, the result of doing work, W, or changing to kinetic energy, K. Or dissipating into yet another form, heat, or Q. All energy is conserved, strictly and absolutely. Again, whatever form it takes, energy, like momentum, is always conserved. Of course, the conservation of energy rules every game, no matter what form of energy is involved, and no matter what the masses of the bodies are. But in this game, there's only kinetic energy, and all bodies have the same mass. What happens when they collide? Momentum, P, is a vector quantity that's the product of the mass of an object times its velocity. In other words, the velocity is equal to the momentum divided by the mass. Kinetic energy, K, is 1/2 mass times velocity squared. Therefore, kinetic energy is P squared over 2m. All of this reveals one of the great secrets, not only of nature, but of how to play winning billiards. When one ball, with momentum, P0, strikes another which is at rest, there are only two possible results. After the interaction, each ball has some momentum, P1 and P2. According to the law of conservation of momentum, P0, the initial momentum, is equal to the final momentum, P1 plus P2. This is a vector equation. The three vectors form a triangle, and in this case, a very special triangle. Remember, in the collision between billiard balls, the only form of energy involved is kinetic energy, ignoring a tiny bit of heat generated by the collision. Not only is momentum conserved, but also kinetic energy is conserved. Since the masses are the same, P0 squared equals P1 squared plus P2 squared. But that's the Pythagorean theorem for right triangles. And as a result, P1 is perpendicular to P2. In other words, when one billiard ball strikes another, which is at rest, they come off at right angles. That's one possible result. But is that the only possible outcome? No. A clever player can make things happen by applying English. In other words, by making the ball spin as well as roll. But even without English, there's still one more possibility. One more way to make a shot that won't work if the balls come off at right angles. If the balls hit just right, that is exactly head-on, both laws, conservation of momentum and energy, can still be satisfied in another way. one ball can stop completely and give all of its motion to the other one. That's the second possibility. This was exactly what René Descartes meant. One ball gives its motion to the other. The total quantity of motion in the universe has been conserved. As theoretician and practitioner, philosopher and mathematician, René Descartes helped as much as anyone to lay the foundations of science. While many of his ideas were criticized then and are dismissed now, his grand vision helped the world to see nature in mathematical terms. Even more than Galileo, as a matter of fact, Descartes saw nature and mathematics as inseparable. Natural science, in his view, should be deduced from axioms and carried out by algebraic manipulation. This begins to illustrate his essential theoretical vision. The trunk of the tree stands for physics, classically rooted in metaphysics, with limbs branching out as medicine, morality or ethics, and mechanics. So all philosophy, wrote Descartes, is like a tree of which the roots are metaphysics, the trunk physics, and the branches are all the other sciences which fall into three principal groups. Within this framework, then, Descartes compared the sciences to a tree. And mathematics, implied here with God, clearly breathes life into his superstructure. More than anyone since Aristotle, Descartes sought an explanation for all worldly phenomena. He tried to find a universal mathematics. In his search for the ideal, he found something more practical: analytic geometry. Descartes introduced symbolic algebra to the geometric manipulations of the ancients and changed the course of mathematics forever.
We've seen our first example today of a kind of process that's extremely important in physics. Two particles come together, interact in some way, and fly apart again. This is cleverly known as a collision. Now, collisions do occur in the real world. If you weren't aware of that, I suggest that you consult your insurance agent immediately. But the question is, why are they so important to physicists? And the answer is that collisions are the only way we have of finding out about the subatomic world. If I want to find out about the nucleus of the atom, the only means I have of doing it is to take two of them and smash them together and see what happens.
And that's exactly what these scientists are doing at Caltech's Kellogg Radiation Laboratory. In a particle accelerator, they can create collisions between subatomic particles, a process that probes the innermost secrets of the nature of matter. But nevertheless, like all other processes in nature, conserves momentum and energy. The Caltech accelerator, like many others around the world, smashes nuclei together at high speeds to make them interact. Negative ions are first created and injected into the accelerator. Their powerful electric forces, adding up literally to millions of volts, will accelerate them toward their target. Inside the chamber, there's a tube through which the ion will pass, from the point of injection to the high voltage terminal and beyond. A negative ion, an ion of carbon in this experiment, begins its journey through the tube. One magnetic field steers the ion around a corner, while another keeps it at the center of the tube. Approaching the high voltage terminal, the ion picks up speed. In the high voltage terminal, a few gas molecules lie in wait. The ion inevitably hits a molecule, and the collision strips off some of its electrons, which gives it a positive charge. And now that the ion has the opposite charge, the same high voltage makes it accelerate toward its target even faster. Carbon ions are directed through an evacuated beam pipe toward the target, helium. This nuclear reaction determines the relative amounts of carbon and oxygen, a crucial step in the evolution of the stars.
The laws that we've used today of conservation of energy and momentum don't predict what will happen in that kind of an experiment. If they did, after all, there'd be no point in doing the experiment. But they are absolutely indispensable for sorting out the complicated things that do happen so that we can figure out what we want to know. This process of studying the microscopic world by means of smashing particles together does seem to lack a certain delicacy. Somebody once described it as being like trying to learn about music by listening to a piano fall down a flight of stairs. But it's the only game in town. It's the only way we have of finding out what happens to atoms and nuclei. And that's why collisions are so important to physicists. Okay, that's it. Try not to have any collisions, and I'll see you next time.
The momentum of an object is equal to its mass times its velocity. When bodies collide, the total momentum remains constant. In any system without external forces, momentum is always conserved.
Funding for this program was provided by the Annenberg CPB project.
You can order these programs on videocassette. Call 1-800-LEARNER and visit us at www.learner.org/channel, the Annenberg CPB channel.